Hello everyone to this lecture of power system stability, and today we are going to discuss the effect of inertia. We have already seen in the previous lecture about the two machine system with losses. Now we are going to consider the effect of inertia on this machine. So for this we need to consider a generator of finite inertia which is feeding power to a finite bus through a series impedance with resistance. Means here the impedance is in series with the resistance for the infinite bus and your generator connection. The power angle curve of constant excitation will be shown in the next figure. The output of the generator is shown by the curve P1 and the power received is at the infinite bus by P2. Thus we can see that the power input to the generator is slowly increased and the generator voltage is advanced in phase. That means what? That by this we are increasing the angular separation, that is your del, which is your rotor angle. Also the output of the generator increases so that it is equal to the input until P1 reaches its maximum value. And when it is going to reach its maximum value? For del is equal to del M1, which is further equal to 180 minus theta 12, and this value should be greater than 90 degree. So the system is stable for all positive values of del less than del M1. We'll see this in the diagram below. So here, as you can see, I will zoom it a bit so that it is more clear for you, that the maximum power received at the infinite bus is given by the value which was del is equal to del M2, which is equal to theta 12, which is less than 90 degree, because previously we saw that it should be greater than 90 degree when we are considering del M1. Therefore, by definition of steady state stability, that the maximum value received by P2 will occur at del is equal to del M2. So we will see what are the actual positions of del M1 and del M2 in this particular graph. So we can see from this particular diagram that when we plot the power angle curve for both the machines, del M1 and del M2, del M1, which is here for this particular graph of P1, is having a value which is greater than 90 degree as described in the previous slide, because P1 is the machine which is injecting power into the bus. Secondly, we can also see that for machine 2 we have this particular graph which is shown by P2, and the value of del M2 is less than 90 degree, which we just saw. So by both these diagrams what we can see that it is a combination of two machines. Machine 1, the machine which is injecting power into the bus, that is your generator, and P2, the machine which is receiving the power, and both are connected by the series connection of R plus jx. Next, we are considering a motor now for finite inertia which is receiving power from an infinite bus. So we are considering which machine? We are considering machine number 2 now. Both again connected through a series impedance. Now for both the curves which we saw in the previous curve, will again apply. Now P1 is the output of the infinite bus and P2 is the input of the motor. We have just reversed the conditions now. So now let the shaft load of the motor be slowly increased. We are slowly increasing the load on the shaft. So what will happen? The motor voltage is retarded in phase now. So that is why what will happen? Your del will start increasing, and also the input of the motor is increasing, so that it is equal to the output until P2 reaches its maximum value. Why this is happening? Because when your motor is demanding some kind of power, it will obviously extract that power from the particular machine which is giving power to it. So it is very necessary that as the motor is increasing its power, it should be equal to output, and this will lead to increasing of del until your P2 is reaching its maximum value, and maximum value is going to occur when again del is equal to del M2. So for the motor load, if it is further increased, what is going to happen? Synchronism will be lost. So we can say that from both the cases, the stability limit is the maximum value of P2, which is occurring at del is equal to del M2 is equal to theta 12, but which is less than 90 degree. So this is how we can see that this case is explaining for machine 2. Then in case of finite motor synchronism, if it is lost, then del will exceed this angle, but in this case what is going to happen? The finite generator del will be increasing its value from del m2 to del m1. We saw in the previous graph also that del m1 was at the leading edge greater than 90 degree and del m2 was less. So with an accompanying increase in generator output of P1 before the loss of synchronism, the generator will therefore become now stable and will be operating at the stability limit of the motor. Now the third case we will consider here is of a motor and a generator, both of finite but not necessarily equal inertias. Both are having different inertias. So what is expected from such a kind of system? It is expected that the maximum stable value, which will be greater than del m2 but less than del m1. The system has reversed now. And the exact value, which will be depending on what? It will be now depending on the relative inertias of the machine, because both the machines are having not equal inertias. We had already explained that. So being near del m2, if the inertia of the generator were high as compared to the motor, and del m1 if the reverse was true. So vice versa is going to happen, that it will be equal or equal when it is near to del m2 if the generator inertia is high, and the reverse will be equal to del m1 if the inertia of motor is high. So that means we can say that reverse is holding true. So from this, if we want to derive a particular equation which should be defining the relation of del with inertia of the machines m1 and m2, we can say that del is equal to del c, which is your critical angle, is equal to tan inverse of m1 plus m2, this, upon m1 minus m2, this, multiplied by tan theta 1 2, the relevant angle between machine 1 and machine 2, where m1 and m2 are what? The inertia constant of both the machines, and the critical angle del c will always be between the angle of maximum sent and received power. So that is why we can say now theta 1 2 will be equal to what? It will be equal to del m2, which is the lowest angle, which should be lying between, del c should be lying between what? Del m2 and del m1, where del m1 is the maximum value, del m2 is the minimum value. Del c lies in between these two, and this value is neither nor equal to theta minus 180 minus theta 1 2. So this holds true vice versa. So what is our approach of this equation of inertia or effect of inertia is that it approaches to del m2 if m1 is very greater than m2, and approaches del m1 if m1 is very greater than m2. So all the three cases we have considered above were for the positive series reactances, and the steady state limit was reached at del is equal to del m2, which we considered as the minimum limit of del. So hence it appeared that del can increase beyond del m2 only up to a value of del c, the critical angle, before the synchronism is lost, because after that the synchronism of the machine will be lost. So what we conclude from today's lecture is that at maximum received power there is a margin of stability which is going to depend upon the relative inertias m1 and m2 being the greatest when machine 2 is an infinite bus. Means here we need to take into consideration machine 2 as the holding power for effect of inertia. So this is what we have for today's lecture. We will come again with a relevant topic to the same particular chapter which we are continuing right now. Till then, study well, stay well. Thank you.